Why do we study quantum mechanics? 3 reasons. The double-slit experiment shows that electrons are waves. The photoelectric experiment shows that light is particles. The black-body experiment shows that energy is quantized. Classical mechanics cannot explain these 3 experiments. Again, electrons are waves, light is particles, energy is quantized. Therefore, we study quantum mechanics to better understand these 3 experiments and these 3 statements. First, double-slit experiment. It shows that electrons are waves. All particles are waves. We can look at this experiment. Very simple. Light passing through 2 slits to create 2 waves. These 2 waves interfere with each other. There is constructive interference, and then you see light band. There is destructive interference, and therefore you can also see dark bands. And again, you can see this constructive, destructive, constructive, destructive, constructive, destructive, and therefore we see dark, light, dark, light, dark, light, dark, etc., etc. If you replace light with water wave, you will observe the same phenomenon. If you replace water with electrons, you will observe the same phenomenon. Therefore, we say electrons are waves. And also, carbon-60 molecules can be used for this experiment. Of course, carbon-60 is much heavier than an electron, and therefore carbon-60 molecules have a much shorter wavelength. How do we know that? There is a de Broglie relation. The wavelength of a particle equals the Planck constant divided by the momentum of the particle. And if we are looking at a baseball, the mass of a baseball is roughly 0.15 kilograms. Let's say one can throw a baseball at 40 meters per second. That's pretty fast. And then the momentum is 0.15 times 40, which equals 6 kilogram meter per second. So we put that 6 on the bottom. On top, that's the Planck constant. It's 6.6 times 10 to the power of negative 34 joule per hertz. So if you use the Planck constant divided by the momentum of the baseball, the result is 10 to the power of negative 33 meters. It's a very short wavelength. That means it's hard to measure or observe the wavelength of a heavy object. 2. The photoelectric experiment shows that light is a bunch of particles. Over here, this is a simple experiment. We're using potassium as the metal sample. It takes 2 electron volt energy to eject electron. This is the work function of potassium. The definition of the work function is the minimum amount of energy that is required to eject an electron from a piece of solid. Usually metal, because it's easier to eject an electron from a metal than from non-metal solid material. So let's see, this is 2 electron volts. And then if we shed a light to the metal, well, sometimes it ejects a photon, sometimes it does not. If you use a red light, the wavelength is 700 nanometers, and then we can use hc over lambda to compute the energy of a photon, which is 1.77 electron volt. And this is not enough to eject an electron. But if we use a green light with 550 nanometers and the energy is higher than 2, an electron can be ejected with a kinetic energy of 0.25 electron volt. How do I know that? It's very simple. It's just the energy of the photon minus the work function 2.0. You get the kinetic energy of the photon. You can use a violet photon with higher energy, 400 nanometers, 3.1 electron volt, 3.1 minus 2.0, the work function. We can predict the kinetic energy of the electron would be 1.1 electron volt. We can convert 1.1 electron volt to roughly 1.7 times 10 to the power of negative 19 joule. And then we know the mass of an electron, 9.11 times 10 to the power of negative 31 kilogram. We can compute the velocity of the ejected electron right here. So again, the kinetic energy is simply 3.1 minus the work function here. All right, so you may ask, why does this experiment tells us light is a bunch of particles? If light is a wave, and if we use a very high intensity of a red light, you can imagine the constructive interference of many waves may create or produce enough energy to eject an electron. For example, just two light waves, you get 3.54 electron volts. That's greater than 2.0. But no, actually a light is just a bunch of particles. They're called photons. And an electron on this piece of metal absorbs just one such particle, or one photon at a time. In this case, if the electron absorbs this red photon, 1.77 electron volt, true, its energy increases, but not enough to overcome the work function 2.0 electron volt. All right. Yes, there are multi-photon absorptions, but it's rare. Another question my students wonder is this. Is there any relationship between work function over here and ionization energy? Because they both involve the ejection of electron. Yes, they are actually similar, very similar to each other. Ionization energy is the minimum amount of energy to eject an electron from an atom or ion. And the work function is the minimum amount of energy to eject an electron from a piece of solid, usually metal. So if you're talking about work function, this electron has to overcome the attraction from not only one nucleus, but many nuclei in this piece of metal. And also, of course, there are many electrons that repel and facilitate the ejection of this electron. So overall, if you take all the attractions from the nuclei and all the repulsions from the other electrons into account, that's the work function. I forgot to mention another student's question about this de Broglie relation. The student asked about this V. What if V is 0? It's very simple. If V is 0, just plug in 0. Lambda is infinity. This particle has a infinite wavelength and thus occupies the entire universe. That's it. 3. The black body experiment shows energy is quantized. First, what's black body? So it's pretty simple. Let's say we make a container, spherical shaped container. We heat it up. We use Bunsen burner to heat it up. Make sure you use metal so the container is not burnt. And then if you heat up metal, the metallic atoms, those atoms vibrates. And there's a certain frequency called the intrinsic frequency of that metal. And then if the temperature is high enough, some of this metal atoms vibrate so fast at a highly excited energy level, and they may jump back to a lower energy level, or even the so-called ground state energy level, or the lowest energy level. And in that process, energy is released in the form of a photon. And we make a very small hole here to allow just maybe 1 or 2 photons coming out at a time. And then we can measure the frequencies of the ejected photon from this black body. It's called black body because mostly it's enclosed, and light virtually cannot escape out of this container, of course, except for this hole. All right, and then if we measure the lucky photons that manage to escape out of the container, we find that the frequency of the photons are always a integer multiple of a base frequency, and that base frequency is actually the frequency of the vibration of the metal atoms. So no matter how many photons you measure, their frequencies would be nu, 2 nu, 3 nu, 4 nu, 5 nu, 6 nu, 7 nu, 8 nu, 100 nu, 200 nu, 201 nu, 3000 nu, but you will never see 1.5 nu. You will never see 1.9 nu. It tells us energy is quantized. At least the energy of these photons are quantized. And later you will learn that in quantum mechanics, as long as your particle or your wave is confined, its energy must be quantized. There are exceptions. What if your particle is not confined? I think in this case, if v is 0, the absolute speed of a particle is 0. It has a infinite wavelength. The particle is a wave with infinite wavelengths. This wave occupies the entire universe, and it's not really confined. And we say in this case, its energy is not really confined. And also there's a spectrum here. I copied this picture from the internet. I think they allow us to use it. Unfortunately, there's no labels for the horizontal and vertical axis. Well, let's say the horizontal axis is the wavelength. This is the number of photons. So basically, you are looking at the probability of observing photons at certain wavelengths, and at different temperatures, you observe different functional values. So at a lower temperature, 1500 K, the peak is at higher wavelengths. At higher temperature, 2500 K, the peak is at lower wavelengths or higher frequency. And now I'm going to show you the classical prediction. The classical classical physics prediction is this dashed line. As the wavelength decreases, the number of photons increases monotonically. However, if you look at the experimental data, as the wavelength decreases, you can see first the number of photons goes up and then it decreases. So this is experimental data. The dashed line is the classical physics prediction. Well, of course they don't match. But if we allow energy to be quantized, so Planck proposed this, and then we use quantum mechanics to make the prediction, the prediction will match with the experimental data perfectly. Therefore, we accept this fact that energy is quantized. And again, I'm sorry about the lack of horizontal and vertical axis. The horizontal axis in here is the wavelength. Over here, this is the number of photons. Or sometimes we can just see the frequency of observing the photons at a certain wavelength. In most physical chemistry textbooks, the authors do not use the wavelength as the horizontal axis. I think they use frequency as the horizontal frequency, as the horizontal axis. Sorry about that. They use frequency as the horizontal axis. Sorry about the confusion. So again, I just got this picture from the internet that allows us to reuse this picture without copyright infringement. Right, and again, I mean, at this low wavelength region, the classical physics completely fails. And I think it's called ultraviolet catastrophe, just to describe the failure of classical physics.